Hello and welcome to the AICE Chemistry Lecture Series. In this video we're going to look at chapter 10.5, which is going to focus on the effects that water has on both the oxides and hydroxides of period 3 elements. So we already looked at a little bit about how these hydroxides get created or how these oxides get created, but let's see how they react with water, because there's a lot of very interesting reactions and interactions between the oxides of the period 3 elements and water. Specifically, one of the big things is whether they create acidic or basic solutions. So let's look at that and get started. So what we're going to look at here is the reactions that the oxides and hydroxides of the group 2, or sorry, period 3 elements are going to have with water. And a lot of these are very interesting because of the acid and basic nature of the compounds. And that's what I'm going to mainly focus on in this section. This section focuses very heavily on whether these oxides or hydroxides are acidic or basic, even going into some reactions of those compounds with acids or bases. So let's get started by looking at the metals here. We're going to look first at sodium and magnesium oxide. Sodium and magnesium oxide had, again, very similar reactions with water. We already discussed how sodium and magnesium by themselves, when reacting with water, would create hydroxides. Well, the sodium oxide and magnesium oxide do exactly the same thing. When a sodium oxide or a magnesium oxide reacts with water, it creates the hydroxide of that element, magnesium hydroxide and sodium hydroxide respectively. So it's the same reaction that we saw with the metals, with just magnesium or just oxygen, just sodium, where it creates a hydroxide, but with slightly different balancing, right? Because now we have that oxygen being involved in the reactant. Well, both sodium oxide and magnesium oxide are what we call basic in nature. Why are they basic in nature? And we discussed this earlier in section 10.3. They're basic in nature because both sodium hydroxide and magnesium hydroxide dissociate in water to give the hydroxide ion. And that's what makes them basic. Sodium hydroxide is more basic than magnesium hydroxide. Oops, that is the wrong setting. More basic, which means higher pH, because it dissociates completely, whereas magnesium hydroxide only partially dissociates. Now, magnesium oxide also is going to react with acids. When magnesium oxide reacts with an acid, what it's going to do is going to create the magnesium ionic compound with the anion of that acid. So in this case, if we use hydrochloric acid as an example, we make magnesium chloride. If we use nitric acid, we will make magnesium nitrate. If we may use sulfuric acid, we will make magnesium sulfate. And on top of that, it will create water. This is a typical reaction of a basic ionic compound. When magnesium oxide, a basic ionic compound, reacts with any acid, in this case hydrochloric, it will create the salt, the ionic compound between the cation and anion of these two compounds, and water in a neutralization reaction. Magnesium hydroxide does the exact same thing. Magnesium hydroxide reacts with hydrochloric acid to create magnesium chloride and water. So whether it's magnesium hydroxide or magnesium oxide, I'm going to here highlight both of these. Whether it's magnesium hydroxide or magnesium oxide, they do the exact same thing. They both react to create the ionic salt of that acid, an ion, and they also create water. So notice, exact same products, right? Everything's exactly the same here because they both essentially do the exact same thing. The only key difference here is the balancing. As you can tell, water here for the hydroxide has a 2, whereas the water in the oxide only creates one water, not two waters. But that's pretty much the only difference here. So we can treat those the same, and as you can see, all of the magnesium reactions are separated by dashed lines here, just to show that they have a common thread. So what is the key here? One, obviously remembering the reactions, and two, remembering that these are all basic in nature. One trick here, and for note taking that you might want to pay attention to, is whenever we're doing this, these reactions are examples, right? We can write these more generically. So if I wanted to write this reaction more generically, the reaction of magnesium oxide with an acid, what I will do is I will do MgO, magnesium oxide, plus the acid is going to be HX, or you can put HY, H, and then a letter of your choosing to represent the anion. So I'm going to choose X, so HX. And then that's going to yield MgX, whatever this compound is. Keep in mind that there might be some subscripts here, depending on the charge, plus H2. And in this way, instead of remembering that hydrochloric acid with magnesium oxide makes magnesium chloride, if they ask you about a different acid, like nitric acid, for example, we can say MgO plus HNO3, which is what that X is going to make MgNO32. We just swap that X for the anion, which is nitrate here, plus H2O. And I believe I need a 2 here. And so this is a more generic way of writing the reaction, but you gotta keep in mind, it's always good to have an example, but keep in mind generics also work very well to look at patterns instead of individual specific reactions. Looking at aluminum now. Aluminum is a weird compound. Aluminum oxide, should I say, is a weird compound because aluminum oxide is actually amphoteric. It is neither acidic nor basic, meaning that when it reacts with water, it won't react, it won't do anything, but it will react with acids and alkalis individually. Alkali, remember, is a water-soluble base. So there is no reaction with aluminum oxide and water. So I'll put that up here. Al2O3 plus H2O does not yield to reaction, so there's no reaction. But aluminum oxide does react with both an acid and an alkali, a base. So we say this compound is amphoteric. Aluminum oxide will react with an acid, like sulfuric acid, to create, again, the ionic compound made between that aluminum and the anion, in this case Al2SO4 aluminum sulfate, and water. So excellent, it reacts in an acid-base reaction, such as a neutralization reaction, creating that ionic compound and water. Aluminum oxide will also react with an alkali, like sodium hydroxide or potassium hydroxide, anything like that, in the presence of water. So it has to be an aqueous alkali, it can be just a base. It needs to be specifically an alkali, so it's aqueous, because remember, that's the definition of an alkali, a water-soluble base. Because aluminum oxide will react with that alkali, like sodium hydroxide, and water to create the ionic compound between, or the complex ion, between the metal ion of the base, aluminum, and 4 hydroxides. This is what we know as a complex. It's a complex between a bunch of different elements here. But essentially what will happen is that whatever this is, so here it's sodium, but it could have been potassium, for example. If it was potassium, then we'll just replace the sodium for potassium here. And it creates this complex with 1 aluminum, 4 hydroxides, and then whatever that metal cation is. Now this does require special conditions. This doesn't just happen. The alkali needs to be very concentrated, that's a condition, and hot. So it needs to have a high concentration of the alkali, and it needs to be heated up for this reaction to happen. But because the aluminum oxide reacts with both an acid and an alkali, or base, we say the aluminum oxide is amphoteric in nature, meaning that it can react with both. Not with water, like we said, no reaction with water, but with an acid, it will make the ionic compound of the aluminum with the anion, and water. With a base, it will make a complex with 4 hydroxides, aluminum, and then whatever the cation is from the base, from the alkali. Now, remember what we said. We had the ionic ones, the metal ones. Now we're moving into the metalloids, silicon, and the nonmetals, the phosphorus, sulfur. Silicon dioxide also reacts with an alkali. Again, silicon dioxide does not react with water. So SiO2 plus water has no reaction, which is probably a good thing because silicon dioxide is what sand is made out of. And otherwise beaches will be blowing up everywhere if silicon dioxide reacted with water. But silicon dioxide does not react with water. However, it does react with an alkali, with something like sodium hydroxide or potassium hydroxide. And again, just like the aluminum oxide, this needs to be hot, it needs to be heated up, and it needs to be concentrated alkali. When it does this, it is going to create the SiO3 ion. So SiO3 will be SiO3 2- ion. And that is going to pair up with whatever the cation from the alkali is, in this case sodium. So in this case we'll make sodium as Na2SiO3 because of the 2- charge, and this is +1 in charge. And water. So this is a very specific reaction, right? It creates this very specific compound here, just like the complex with the aluminum. Do remember that both of these are aqueous, meaning they're both soluble in water for their properties. Not properties, sorry, for their states of matter. But it creates this Na2SiO3. The SiO3 2- ion is really what's created, and it just happens to pair up with whatever this cation is. Phosphorus oxide, so the P4O10, the tetraphosphorus decoxide, is going to react with water, as do the sulfur ones, to create an acid. So we say these are acidic because they're creating acids. In the case of the P4O10, it reacts with water to create phosphoric acid. SO2 reacts with water to make sulfurous acid, H2SO3. And SO3 reacts with water to make sulfuric acid, H2SO4. So all three of these are going to be acidic because they create acids when reacted with water. Whereas the silicon dioxide does not react with water. The reason we call the silicon dioxide acidic is because it reacts with an alkali. So realistically speaking, those are the two choices, right? And a basic nature compound can be basic because it reacts with water to create an alkali, like magnesium hydroxide or sodium hydroxide. Or it can be basic because it reacts with an acid, just like the magnesium oxide, magnesium hydroxide. A compound can be acidic because it reacts with a basic compound, like silicon dioxide reacts with sodium hydroxide, or it can be acidic because it creates an acid in the reaction with water, like the P4O10, sulfur dioxide, and sulfur trioxide. And then for amphoteric compounds, which the only one here is aluminum oxide, it's amphoteric because it can react with both acids or alkali bases. But why does this happen? Why is this the case? Well, in order to look at the acid-base nature of the oxides, we need to look at what they make. And again, I kind of went over this already indirectly, but we say sodium and magnesium oxides are basic because they create alkalis with water. And again, those alkalis, those bases are respectively NaOH, sodium hydroxide, the most common alkali, and magnesium hydroxide, MgOH2. So because when reacted with water, they create bases, they're basic. We call them basic. So that's what these two are. Aluminum oxide, on the other hand, is amphoteric, which again means that it can behave as both an acid and a base, because it reacts with both acids and bases. As we saw earlier in the year, an acid is an acid because it can react with a base. And a base is a base because it can react with an acid. So a compound that is amphoteric can do both and therefore react with both. And so that's why aluminum oxide is amphoteric. Not because of its reaction with water, because there is no reaction with water, but because of its reaction with acids and bases. Silicon dioxide reacts with a hot alkali. So again, there is no reaction between silicon dioxide and water, but because silicon dioxide reacts with an alkali, we call it acidic. And then finally, the rest of them, the covalent compounds, the P4O2, SO2, and SO3, those are acidic because of the reactions with water. These create acids with H2O. This one creates or these two create bases with water. The silicon dioxide reacts with a base, which is why we call it acidic, whereas the aluminum oxide reacts with both an acid and a base, which is why we call it amphoteric. So if you notice by now, the sodium oxide and the magnesium oxide are ionic in nature. So these are ionic. Oops. In nature, whereas the acidic ones here are covalent in nature. And then the only one that doesn't fit that pattern, right? Because these are all covalent. SiO2, P4O10, SO2, SO3. These are all covalent. Granted, this is giant covalent, and these are simple molecular, but all covalently bonded. The sodium oxide and magnesium oxide are ionic. You would think that the aluminum oxide, which is ionic, or which is amphoteric, which is ionic, would be also basic. But it's amphoteric because of something we discussed earlier in the year. Just like aluminum chloride, aluminum oxide has a bit of both. It is an ionic compound with a covalent nature. And this amphoteric nature kind of hints towards that. It's showing us that even though this is ionic, it is a little bit covalent. And that's why it's amphoteric. Because if we go back to what we were looking at earlier, notice how the acid reaction and the base reaction both happen because they are, I said that backwards. The basic reaction and the acidic reaction both happen, but the basic reaction does not require any special conditions, while the acidic reaction does. And again, that's because, went wrong way. That's because the aluminum oxide is ionic, so the basic reaction happens very easily, but it has a bit of covalent character, which is why the acidic reaction happens, but it requires more harsh conditions. Now let's look at the structures of these oxides. And this, again, we touched upon it, but the electronegativity of oxygen is 3.5. We said it's the second most electronegative element on the periodic table. And as such, when it pairs up with the elements on period 3, it's going to use that electronegativity difference to see whether they're going to be covalent or ionic. Since the difference between the oxygen and the metals, aluminum, sodium, and magnesium, are the farthest, are the most drastic, those are all ionic. Whereas the difference between silicon, phosphorus, sulfur, and then the oxygens are less different, or there's a smaller gap, those are going to be covalent, although still polar, but covalent. Well, that structure and that bonding is what guides their reactions and all of the explanations we just saw. Sodium oxide, magnesium oxide, aluminum oxide, silicon, phosphorus, and the sulfur oxides. As we go from left to right, we go from ionic we go from ionic to covalent. And this is a bit of a spectrum, right? We go from left to right, from ionic to covalent. As we move from left to right, they get more covalent. So the sodium and the magnesium oxides are very ionic. They have giant ionic structures. And they have very good electrical conductivity when they're dissolved in water and have very high melting points. The aluminum oxide is ionic, but with a degree of covalent character. So we still have the giant ionic structure, but with a little bit of covalent character, which means that it's still a good conductor of electricity when dissolved, and it has a very high boiling point, or sorry, melting point. And that's why, again, these are going to be basic, and this is amphoteric. As we keep moving across, the silicon dioxide is now covalent. But it's not just covalent, it has a giant covalent structure. That giant covalent structure makes it so that its melting point is the highest out of any of these. It is the highest melting point out of the period 3 oxides. Because a giant covalent structure is very hard to break those covalent bonds when we melt it. And also the reason why it does not conduct electricity when dissolved in water or in the liquid state, because this is not ionic, so it's not going to conduct electricity. And then we have the covalents, right? The P4O10, SO2, and SO3. These are simple molecular, which mean that, again, the electrical conductivity is non-existent in the liquid state because they are just covalent compounds. But notice how the melting point is now extremely low, because these are not held together by covalent bonds. They're held together by intermolecular forces. And those intermolecular forces are really easy to break. So notice the trend. We go from high to really high melting points, but then it plummets once we get to those simple molecular structures. We have really good electrical conductivity with ionics, but then once we get to the covalents, no electrical conductivity in the melted state. All of these patterns, the acidity, the relative melting point, the electrical conductivity across period 3 can all be dictated by their type of bonding and also their structure. Because remember, it's not just all the type of bonding, otherwise the covalent ones will all be the same, but it's also about their type of structure, whether it's simple molecular or giant covalent for the covalently bonded compounds. But that's it. That's the properties, some of the chemical properties of the group, the period 3 elements based on their structure, as well as the reactions we saw earlier. That is it for section 10.5. I'll see you all in the next video to discuss the chlorides of the period 3 elements in 10.6.